Welcome back. In this last part, we're going to do a couple more examples. We're going to do some involving some playing cards next. So for example 9, we are looking at dealing some 5-card poker hands. And so just a reminder, when we're talking about playing cards, when I'm giving you a hand of cards, that's just a collection. We're not putting them in any sort of an order. This will just be some combinations. We might also need to, if you need to, refer to the earlier sections on the terminology for playing cards. You might need to revise that. So if we're remembering when we first talked about playing cards, basically for every card there's two things on it. There is a suit, so clubs, hearts, diamonds, spades, and there's what we either call a denomination or a rank. That's the number that's on the card. So when I'm looking at making my selections of cards, I may have to start thinking in terms of suits and also ranks. One other thing I want to just point out before we get into the question, I'm not expecting anybody to know rules for card games. So you'll see some terminology here like full house. You won't need to know what a full house is. I will describe what that means. So if there's any special game terminology you need to know, I will let you know what that means. So let's start off with the first one, the easy one, which is the no restrictions. Generally, for most of these questions, for counting questions, no restrictions is usually a pretty fast and easy thing to do. And in this case, very easy to do because out of the 52 cards in a standard deck, we are, as an action, just selecting 5 of them. So 52C5. Which is just a little over 2.5 million. 2,598,960 possible 5-card hands you could be dealt. Okay, so now let's get into ones where we do have restrictions. First one, we're looking for selecting a pair. And so to have a pair, you have 2 cards with the same denomination, same rank, and then the other 3 are all different. So I'm going to give an example of a pair. Might be you have a 2 of hearts and you have a 2 of diamonds. I cannot draw a diamond very well. There we go. That's better. And let's say you've got a 5 of hearts and a 7 of hearts and a 9 of diamonds. There we go. That would be something that would be a pair. So you have 2 things with the same number on them and the other 3 that are all different. So just like the scarf question from before, where I said that raises, once we know what a picture of it looks like, it raises some questions that we'll have to ask ourselves for counting. So in this question, I've got a bunch of things I need to ask myself. So first off, I know that if we're thinking about all the different numbers that we have, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, all those ranks and denominations, one of them is going to get used for a pair, and 3 of them are being used for single cards. So I have some questions to ask myself. So the first one I might ask myself is, which rank or which denomination is being used for the pair? So I have 13 ranks in total. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. And I need to select one of them to be the rank that's going to be the pair. So at this point, I've decided it's going to be a pair of 2s. And then you now need to decide which of those 2s are going to be your pair. You need to decide which of the 4 suits are you going to have. Is it going to be hearts and diamonds? Is it going to be clubs and spades? What is it going to be? So for the pair of 2s that I've decided, I now need to choose 2 suits. So out of the 4 suits, clubs, diamonds, hearts, and spades, I need to select 2 of them. Okay, so that's taken care of the first 2 cards. I've chosen that it's going to be a pair of 2s, and now I've chosen it's 2s that are a diamond and a heart. I now have the last 3 cards to deal with. I still have a choice. I have several choices actually left to make. I need to know, for the 3 remaining cards, what are their ranks going to be? So I need to choose ranks for the single cards. And I'd say, well, okay, I already used up one of these ranks. I can't use twos again, because if this was a two or a two or a two, then I wouldn't have a pair. I'd have more than a pair. So I don't have 13 ranks to work with anymore. I only have 12. And I need to select 3 of them so that I have 3 different ones for my 3 cards. So 12C3, that's me choosing my ranks. So now I've decided my last 3 cards are a 5 and a 7 and a 9. Okay, good, good, good. We still need to decide on suits. So for the first of the 3 cards, we need to choose one suit. So 4 suits, I'll choose one of them. So at this point, the 5 and the heart has been chosen. Great. I still will need to choose a suit for the second one. So out of the 4 suits, choose one for the second one. And so at that point, I've chosen its hearts. So the 7 of hearts, that can be put to the side. Great. I know the last card is going to be a 9. I don't know what kind of 9 it is. So again, I need to choose a suit. So just to summarize, we decided which rank was going to be the pair, then we chose suits for the pair. We decided which ranks will be single cards, then we chose a suit for a first one, a suit for the next one, and a suit for the last one. And all total, that gives us a grand total of number of selections being 1,098,240. Before I move on, one thing that you might be thinking about, and this is something people will sometimes do, they might say, couldn't I have done 12C1, choose one rank here, and then 11C1, choose one rank there, and then a 10C1, choose another rank there? Why do I choose all 3 single cards at the same time? The reason I'm doing that is because we're not putting our cards in any sort of an order. So for the 3 single cards, I have no idea what order they were dealt in. Did I get the 7 first, or the 5 first, or the 9 first? There's no way to tell, because again, these cards are not being put in any particular order. So I'm not choosing the ranks for the single cards separately. I'll say, well, I need 3 separate ranks, and I'll grab them all now. So 12C3. Okay, next one up. The hand is a flush. So flush means that all the cards have the same suit. So it's all diamonds, or it's all clubs, or it's all hearts. So here would be a flush. This would be 2 of hearts and a 7 of hearts and an 8 of hearts and an ace of hearts and let's say a king of hearts. There we go. That is definitely a flush. They all have the same suit. They will all have different ranks, of course. You wouldn't be able to have 2 identical king of hearts because there's only one king of hearts in the deck. So if everybody was hearts, you could have as many as one of everybody. That's it. So that means I'm going to have 5 separate ranks that I'm going to need. So I guess that's my first question is, which are my 5 ranks? Because a flush has to have 5 separate ranks in it. And again, since it's 5 individual cards, I'm not going to choose a first one, then a second, then a third, then a fourth, then a fifth, because I'm not putting these cards in an order. I'm just making a collection of 5, so it doesn't really matter which was the first or which was the last. So out of the 13 ranks, I will just choose 5 of them. Good. So now at this point, I've decided that it's going to be a 2, 7, 8, ace, and a king. I still need to know what suit it is. So I still need to choose a suit. Now here's the good news. I only need to choose the suit once because all the cards are going to have the same suit. So whatever suit I choose for the first card, that's going to be the same suit for the remaining cards. So I only have to choose the suit once for C1, and once I've decided that the first card is going to be a heart, then automatically, if I want it to be a flush, all the rest of the cards have to be hearts as well. So not that many flushes in a deck, 5,148. Okay, full house. Full house means three with the same denomination and the other two with the same denomination. So something like an ace of hearts, ace of clubs, and an ace of diamonds. I cannot draw a spade. I couldn't draw clubs very well either. So I have three aces and let's say two hearts, and two diamonds. There we go. That would be something that's a full house. I have three cards that match each other as far as the ranks or denominations go, and then two cards that match each other as far as ranks or denominations. So, bunch of questions to ask myself. I need to first ask myself, which rank is going to be the one for the three of a kind? So a rank for the three matching cards. Out of the 13 ranks, I'll choose one of them. So at this point, that's me deciding it's going to be three aces. Then I would have to decide which aces. I would have to choose the suits for those aces. So out of the four suits, I would need three of them. So suits for the three cards, that's my next choice. So I have decided it's going to be rank was aces, and then I chose the suits as hearts, clubs, and diamonds. So now the first three cards have been taken care of. This still leaves the last two cards to take care of, so I need a rank. There's 12 ranks left, and I need one of them for the pair. And then I also still need to decide, once I've decided, oh, it's going to be a pair of twos, which twos. So I then need to decide suits. So a suit for the two suits for that pair. And that can be done in 4C2 different ways. So 13C1, we chose the rank for the three of a kind, then 4C3, the suits, then 12C1, the rank for the pair, and 4C2, the suits. That gives us 3,744 possible ways to select a full house. All right, let's do one last example. This one involves making passwords for a website, and for this website, it only wants you to make a password of a length of 5. All we've got to work with here is the 26 lowercase letters of the alphabet and the 10 digits from 0 to 9. That's it. So you don't allow yourself to use any question marks or capital letters or any other symbols, just those 36 things. So if we're thinking about no restrictions and I'm thinking about creating a website password, I have password is of course going to be in some particular order, because if your password was 12345, that's not the same password as 54321. So there is an order that will matter to this. So I might expect to see a factorial in the future, or maybe a permutation, or maybe multiplication principle. And at least for no restrictions, I'm going to think about using the multiplication principle, because I just need to fill in my password from the first letter or first character until the last one. And for each of those, I just have to make a choice as to what I'm going to fill it in with. So if I have no restrictions, I have any of the 26 letters and any of the 10 digits, I've got 36 choices for the first, second, third, fourth, and fifth places. So 36 to the power of 5, or just a little over 60 million, 60.5 million almost. 60,466,176 possible passwords. All right, next one up. We want no character can be repeated. So can't repeat a letter, can't repeat a digit. So if we're thinking about this, I could do this with the multiplication principle. I could say you have 36 things, and then 35 because you've used somebody up, then 34 because you've used up a couple of things. You could do it that way. Or if you're feeling clever, and I'm feeling clever at the moment, we could think about doing this in one step with a permutation. Because if you're thinking about this, to have no character be repeated, you would have to select 5 different characters, because That's how we would have nothing being repeated. And passwords have an order to them, so those 5 characters would have to be put into some sort of an order. In other words, out of the 36 things that we have to work with, I'll select and arrange 5 of them. And that would be the way to do it in one step. And that's 45 million and 239,040 possible passwords are left. So if we allow ourselves to repeat things, we've got over 60 million passwords. If everything needs to be different, then 45 million thereabouts. Okay, so further restrictions. Again, when we're doing a follow-up question, it doesn't necessarily mean that the earlier parts carry over. So part B was nothing gets repeated. That doesn't affect part C. So these 3 letters followed by 2 digits, maybe things are repeated here, maybe not. So for C, a password like AAA22 would be fine because it doesn't say anything about repetitions. All I know is that the first 3 positions are letters, and then the last 2 are digits. So I'm again thinking about multiplication principle and just filling things in from left to right, the first, second, and third positions, and then the 4th position and the 5th position. And if it has to begin with letters, then 26 choices for each of those first 3 places. And the last 2 things need to be digits, so 10 choices for the last 2 positions. So you have 26 cubed multiplied by 10 squared, or just a little bit under 2 million. 1,757,600 possible passwords. Okay, so has to begin with 3 letters followed by 2 digits. What if it has to contain 3 letters and 2 digits in any order? So now those 5 things could be wherever. So for this, if we're thinking about it, now there's new questions that we might need to ask ourselves. I've got 5 positions that need to be filled, and I know that 3 of them are going to be letters and 2 of them are going to be digits. The question is which 3 and which 2? So I guess my first task that I'm thinking about here is I need to choose where do the letters go? So out of the 5 positions that I have, I'm going to need to select 3 of them. So to choose 3 things out of 5 things, that's 5C3. So I might decide, for example, that a letter is going to go here and here and here. So now I need to start filling in those positions. I need to fill in the first letter, second letter, third letter. And just like before, if there's no restrictions on repetition, then you'd have 26 choices for the first letter and 26 choices for the next letter and 26 choices for the next letter. Once I've chosen where the letters go, then automatically the 2 leftover spots, those need to be numbers. Those need to be the digits. So I don't really need to choose where do the digits go. I kind of already know where the digits go. I just need to choose which 2 digits I'm using. And in the first position, you'd have 10 choices, and in the last position, you'd have 10 choices. So we really wind up with something similar to the previous example, just with a little 5C3 in front. And that gives us 17,576,000 possible passwords. So we looked at what if it was 3 letters and 2 digits, 3 letters at the beginning? What if it's 3 letters and 2 digits, 3 letters anywhere? And now finally, what if it's 3 letters and 2 digits, the 3 letters are anywhere, and on top of that, no character can be repeated? So let's do that. Let's start off with the first part. I'm going to first think about my first task. Same as before, we have 5 positions, and I need to know where do the letters go. So I need to choose locations for letters. So 5C3. So this is me choosing that a letter will go here and here and here, and then I can just fill in those positions. You could do this with multiplication principle, saying you'll have 26 choices, then 25, and then 24. Or if you're feeling clever, you could use a permutation. You could say, out of the 26 letters, you're going to need 3 different ones and put them in some kind of an order. In other words, P26-3. And similarly for the remaining 2 positions, again, we don't need to choose where the numbers are going to go because we already know where the numbers are going to go. Once we've chosen where the letters go, then the 2 remaining positions, those are the positions for the numbers. So now I'm just slotting in those 2 numbers, and I'm going to say to myself, well, I could say 10 choices for here and 9 choices for there, or I could use a permutation to do all the work for me and say, well, you have 10 different numbers, and you're going to need to select 2 different ones and then put them in some sort of an order. That's P10-2. So looks like we have 14,040,000 possible passwords where there's 3 letters, 2 digits in some kind of an order, and nothing is repeated.